Where we ended on Monday was looking at our addition reactions with the Cyclo tri intermediates. So forming a three-membered ring. Did you guys have a question? No? And with those three-membered rings, if they continued on to a secondary step, the nucleophile would have to come in from the back side to eject your electrophile. Right? In these cases, your initial electrophile has the secondary ability to also act as a nucleophile. That's how we end up with a three-membered ring. Depending on the stability of that three-membered ring, it can undergo a second reaction with a stronger nucleophile for that backside attack. Right? So we could see these reactions then stack on top of each other. Right? So if we look, bromine is one of these such electrophiles. So the bromine would go through and react, and if we looked at our intermediate, we'd be having the bromine where that electrophile is. Problem with that is, what charge would the bromine be? Positively charged. Does bromine want to be positively charged? No. So with this initial reaction, we're going to see this followed by a second one. And we're going to have another nucleophile come in and react. Okay? That nucleophile can be virtually anything I want it to be. Typically, you see it as bromide, the counterpart to our bromine. Okay? Or you'll see it as some kind of oxygen-hydrogen compound with either with either hydrogen or a carbon coming off the other end. We need to have that hydrogen there so that we can stabilize the forming oxonium ion. Right? CH2N2. Believe it or not, that also fits in this one. That one gets a little bit weird, but it becomes a little bit more apparent once we draw out a Lewis structure. So if we were to draw out our Lewis structure, carbon, hydrogen, hydrogen, nitrogen, nitrogen, there's our basic structure. Nitrogen has 5 valence electrons, so we bring in 10 from there. Carbon's 4, plus the hydrogen 2. We get a total of how many electrons? 16. How many do I currently have drawn in my structure? 8. So I could go through and start placing electrons. That would then be the next number. 10, 12, 14. And we could try and get away with 16. Why would we go to the nitrogen first? It's a more electronegative element. We notice we're missing octets, so we would try and fix that. And if we did something along those lines, we're going to have all sorts of other issues. We'd end up having a forming positive charge on that carbon, and we'd have a formal negative charge on that nitrogen. Okay. Is there a better way to arrange those electrons? Yep. What's that better way? Place the lone pair on the carbon instead of that central nitrogen. Form a triple bond with that nitrogen. This is now a better structure because every single atom has its octet. Okay. This has some interesting features coming out of it that may not be readily apparent until you, say, draw formal charge. You have a positive nitrogen and a negative carbon. Okay. Does carbon want to be negative? No. So that is now extremely nucleophilic. Does that nitrogen want to be positive? No. So it's going to start withdrawing electron density as quick as it can. Where's the easiest place for it to get those electrons? We could try and go from the pi bond, but that means nitrogen stealing electrons from nitrogen. Does it want to do that? No. So it's probably easier to steal them from the carbon. What would the end result be? Do I have too many electrons on the nitrogen? Whoops. Let's pull this. Pull that down. No, the nitrogen has its octet satisfied. Not only does it have its octet satisfied, it's now neutral. And I formed N2. What is special about N2? It's a gas. It's an incredibly stable gas. If we're going to run reactions under inert atmospheres, one of those common atmospheres is nitrogen. Okay, we just pump nitrogen through the system. Okay, the nitrogen tends to not react with things. So that is a phenomenal leaving group because it generates something incredibly stable. Not only is it incredibly stable, as a gas, it bubbles out of the solution. We literally can't reverse the reaction because the reactant isn't there anymore. Right? What else comes out of this? We get this goofy looking structure, which honestly I swear I did just circle, but there's a slight delay in the recording, and it's probably going to tell me I'm not connected anymore. Yeah. What's the issue with that carbon? It has a lone pair. Well, a carbon with a lone pair would be what charge?
That's neutral.
Okay, we might immediately jump all over negative. Okay? A carbon with a lone pair and 3 bonds would be negatively charged. Does that have 3 bonds? No. So if we go through and calculate the formal charge on that carbon, what is it? It's neutral. It doesn't actually have a charge. What we've generated in that carbon structure is something known as a carbene. Okay? Incredibly reactive, tricky to deal with, all sorts of fun stuff behind it. Why is it reactive? Can carbon stabilize a lone pair? No, it's not electronegative, it's not large. It can't stabilize that lone pair very well. What else is the issue with this carbon? No octet. So this carbon has 2 things going against it. One, it's missing its octet. So what does it want to do? Find electrons. It wants to accept electrons, meaning that carbon can act as an electrophile. It can't stabilize the lone pair. So what does it want to do with that lone pair? Get rid of it, which means it can act as a nucleophile. We have the perfect case to be forming our 3-membered ring. Okay? There's those who are being like, God, I really hope I don't have to see that. It shows up kind of rarely. Okay? One of the reasons why it shows up kind of rarely is that it's fun chemistry. I mean, it's neat. Like, cool, carbon can do 2 things at once. That's fun. Okay? But it tends to not show up very commonly in synthetic labs. Okay? Why would we not do this reaction? It's actually a phenomenal yield. It works really well. How good of a leaving group was N2? Really, really good. It is so insanely good that what is that bond really trying to do? Break off. Okay? So that I can form this incredibly stable product. So really what I'm looking at is a product that is very low in energy, which means the reactant is really high in energy. So if I drew out an energy diagram, I'm looking something along these lines. Why might that be synthetically problematic? Where did all that energy go? Okay. It usually gets released as heat, and if you don't run the reaction carefully enough, that heat is enough to cause explosions. Okay. If we think back to the glassware that we use in our labs, we have those ground glass joints, right? They form a nice airtight seal, keeps everything nice and trapped. This reagent is so reactive, you can't use that glassware. Because if you use that glassware, it reacts with the glassware and explodes. Okay? You have to use insanely polished glassware. Okay? It came down to actually me doing this in lab. I was actually going to do one of these experiments, and my advisor said, no, you can't do it. I was like, okay, I guess I'll try and find something else. But the research associate of the lab that has been working in OChem for probably 40 to 50 years, amazingly good chemist, very, very good, volunteered to do the experiment, and the advisor still said no. Okay? The reaction itself is insanely dangerous. Okay? People that work with this reagent are missing fingers, if not their lives. Okay? So, kind of neat in that respect. That tends to be one of the reasons why we talk about it. Okay? It's known as diazomethane. Azo is in reference to the nitrogen. Okay? So diazo, because there's 2 nitrogens, and then we have a methane. Okay? So your diazomethane reactants tend to be very, very dangerous to work with, but they can form these awesome little 3-membered rings. Okay? We can form cyclopropanes. It's one of the only ways we can form a cyclopropane. Okay? So it's neat in that respect. That's typically why it gets talked about. You also tend to see it because students tend to freak out at that carbon structure and say, well, it must be charged. This is why we have formal charge rules. Okay? Follow your formal charge rules, you're fine, you'll get to the correct answer. This is why we talked about them, stick with them. Okay? Would we expect a secondary reaction with this one? So if we get rid of, we're going up on the upper left-hand side. If I put that carbon in there with the two hydrogens, would I expect a secondary reaction? Okay. That second step. Would I expect a nucleophile to come in and attack? If it came in and attacked, what would happen to that red carbon? It would exceed the octet, so what has to happen? You'd have to break a bond. Is that a good bond to break? Why not? That would form a negative carbon. That's not a good leaving group. Okay? So this reagent does not continue on as shown at the bottom. It stays at the cyclopropyl structure. Okay? We don't have that good leaving group. Okay? Another reagent that pops up, this one's super common to see as well, okay? MCPBA. Okay? Or this is actually not shown technically as MCPBA, but you will see it written as MCPBA, and all it's talking about is really this functional group out at the end. When you look at that structure, what do you see as the reactive bond? Okay? There's a reference to the hydrogen bond being weak. Why is that bond going to be weak? Oxygen's more electronegative than hydrogen. Fair enough. I would make an argument that this bond is even weaker. The red one. Why is that bond weaker? Oxygen's the second most electronegative element on the periodic table. I put two of them next to each other. What are they going to do with those electrons? They're going to be constantly fighting back and forth with them. Okay? If we look at this as red versus blue, which of those do you think would win? Red. Why would red win over blue? We could go through and compare that red has carbon on its team versus hydrogen. And what's the difference between carbon and hydrogen? Carbon is slightly more electronegative. Okay, so we could make that argument, but that's slight. That's not a very big deal. Also not going to be a huge deal because that carbon can't stabilize that negative charge. What else does that carbon have next to it?
The other oxygen.
We have that other pi bond and that other oxygen. That other oxygen is incredibly electronegative, meaning it pulls those electrons away. Okay? Which makes that carbon very positive. Oxygen, being the nice guy that it is, will share across. We have a phenomenal leaving group on the red-hand side. What does that then make the blue? Why would it be a nucleophile? Okay. So one of the things that could help is if we drew out the result. So one of the things that I'm trying to get you to go through and do is draw out your arrows and draw the results of those arrows and see what you get. Okay. And so one of the statements that I heard is, well, we have OH, and OH is a phenomenal nucleophile. Yes, when it's hydroxide. I completely agree. Is that what my instructions say? No. The instructions say that that pair of electrons goes away from the oxygen. What I have instead is an oxygen looking like that. What is the issue with that oxygen? It's missing its octet and positively charged. Yes, it can still act as a nucleophile because lone pair electrons. It can also act as an electrophile because missing its octet. Okay? That structure cannot form on its own, okay? Because oxygen can't miss its octet. So something has to force that red oxygen to steal the electrons away. That something would have to be supplying electrons, kind of like a pi bond. So those electrons are what initiates this cascade. Okay? We would then be forming a positive charge on one of the carbons of our pi bond. I want to stabilize that positive charge by giving it electrons from the oxygen. But then the oxygen would be positively charged because of the bond to the hydrogen So in this giant cluster of reactions, all of this happens simultaneously. Right? The result, the end of that step, if we go again to our upper left-hand corner, would be that structure. Would I expect a secondary reaction, at least right away? Is this a good leaving group? If it left, what charge would it become? Negative. Is a negative oxygen a good leaving group? No. Okay, so I can't get an immediate nucleophilic attack. I'd have to run some other chemistries to help force that to act as a leaving group. Okay? The functional group we've generated there is an epoxide. Epoxides are synthetically very useful. Okay? So they are super commonly tested on. That's why you need to be aware of this reagent. It can get written out as MCPBA, okay, or metachloro peroxybenzoic acid. Okay. Do you need to know that? Probably not. If they write it out, look for the letters and try and come up with an acronym, MCPBA. The other way it can get written is as shown with the structure. That would be insanely nice and generous. Typically, they aren't nice and generous, and you see it written as some R group CO3H. How do you get 3 oxygens bound to each other? You don't. You get the peroxy functional group. Okay? So the O3 is a tip-off that you're getting this kind of system. Okay? You may not be happy about it, but you do have to accept it. You're looking for these kind of patterns and trying to come up with predictions behind them. The other common one that fits this same kind of pattern is mercury, okay, or mercury acetate. Mercury's got a special functionality in that it has a lone pair. Cardi thankfully shows the lone pair in most cases. So as a lone pair, it can act as a nucleophile that satisfies one of our conditions. What do we have in the O acetate? Sorry, I should have drawn that in blue. We have a phenomenal leaving group due to resonance stabilization. The mercury can act as both an electrophile and a nucleophile. It satisfies the conditions to generate our 3-membered ring. That 3-membered ring would look like this exciting little guy. Is that a particularly stable structure? No, why not? Positive charge. So is that a good leaving group? Yep, it's great. All I need is a weak nucleophile, can come in, do backside attack, kick that out, and I would continue on to the next stage. Okay? So again, we're trying to find patterns and group reagents into certain classes so that we can then determine something about what those products will look like. Okay? If we don't do this, which is fine, we don't have to, it's now strict memorization. So what I'm trying to do is set you up with some kind of characterization to help you with that. Make sense? Enough? Make sense enough? One person, good enough. Okay. Does your 3-membered ring continue after that? Okay. So deciding on if a second step is necessary for your mechanism, you have to go through and ask, is that 3-membered ring more stable or less stable relative to any nucleophile that is present? Okay. So if you have an incredibly strong nucleophile, well then you'll probably see a secondary step. If you have a weak nucleophile, then what needs to be true of your leaving group? It needs to be a good leaving group. So what we're looking at is that intermediate 3-membered structure and deciding, is it a good leaving group? Well, is it positively charged? Yeah. If it acted as a leaving group, what would happen to the positive charge? It would become neutral. Which is more stable? Neutral or charged? Neutral. We have a great leaving group. A weak nucleophile is all we need. What if our 3-membered ring is actually neutral to start? it would then be negative when it leaves. Is that a good leaving group? No. Right, which means I can't use a weak nucleophile. I would have to use a strong nucleophile, which more than likely wasn't present in solution, because if a strong nucleophile was present, what would it have reacted with? The Lewis acid instead of the alkene. Okay? So what we're trying to do is think about those stages and look at where all these things can connect with. Okay? So if it's stable, stop your reaction. If it's unstable, do a nucleophilic attack. If you're not sure, do the nucleophilic attack anyway. Look at what that leaving group was. Compare that back to the nucleophile. So you can always draw it out and decide later. Okay? So if we go through and take a look at this first one. Okay? There's my three-membered ring. There's the presence of my nucleophile. Do I have a good leaving group? Well, if I don't know, run the attack. There's my nucleophilic attack. Kick out the leaving group. What would I get? And a negative oxygen up there. Everybody agree? Okay. Well, which is more stable, that negative oxygen or that negative oxygen? Okay, the one in the red box is more stable. Why? Resonance. You mean I have to evaluate charge, size, electronegativity, resonance, and induction? Yes. That's how you predict these reactions. Okay. Otherwise, it's raw memorization, which is cool. That's fine. I can't do that. Okay. And I also can't teach you to memorize. Okay. So what I'm getting you to try and think about is those results. Draw out those results. What about the next one? Okay, so that first one, we would expect it to stop. No chemical reaction occurs. How about the next one? Well, since I don't know, let's go through and run the reaction. What would the result be? Where's my leaving group? Top bromine, bottom bromine. I heard it, top. So I'm comparing that top bromine to the bromine in the box. Which one's more stable? Probably out of the box. Why? Not charged versus charged. Rule number one in stability, not charged is more stable. What happens? This reaction continues. It goes to become out of the box. We have to run the nucleophilic attack. So in our drawing, if we looked at that, we'd say, well, they're identical. There's no way to tell. Okay? However, what we're trying to do is draw our product in such a way that we can see it from our original drawing. The purple bromine is which of those two bromines? Probably the bottom one. Why are you able to guess that if they're identical? The way that I drew the arrows and the way that I drew the product. I drew them to match as much as possible, minimize any kind of rotation, spin, or flip of the structure, so that when I look at the result, I can make those comparisons. Because you're right, those are identical bromines in this situation. I would have no way of knowing that unless I locked that into my drawing. Okay? Which I did a pretty decent job, if I do say so myself, because you said that the bottom bromine was the purple one. Okay? So your drawings become very important to being able to advance and predict what's happening. If your drawings are, nicely put, bad, it becomes very difficult to use your drawings to answer questions because you're basing your answer off of a bad structure. This is why we go all the way back to Unit 1 and we talk about proper bond angles when we draw out structures, because it helps us answer questions. That's why you're supposed to be doing it. Not because we want to make it look pretty, because it helps us answer. Make sense? Next one. So the middle box continued. First one stopped. How about the last one? What do you think? Did it continue or did it stop? Stopped. Why'd you say stopped? The product is less stable. I don't accept that answer, and I talked over a bunch of other people talking. Your turn. Go ahead. Okay. Carbon can't stabilize the lone pair. What lone pair? So what you're evaluating is good. I like that. Okay? But what you're talking about is something that you haven't drawn yet, that isn't visually there. Okay? And that's good. You're starting to image that, and you're seeing that in your head. I do like that. Okay? But I'm also trying to get you to recognize some other pattern. What other pattern could you look at to suggest that this one should stop without having to draw anything out? And don't tell me, well, I drew it out. I didn't draw anything out. I just know the carbon's negative. You still drew it out in your head. You can't do that. The neutral didn't continue forwards. Charge did. So if you can do enough of these questions and look at those intermediates, you can start to make those conclusions without having to draw them out. Okay? So there's multiple pathways to getting to the same concept. Make sense? Okay. So, your turn. Predict the product. See what you can start. You should be looking at these structures and it should start becoming fast. When you look at that starting material, how many carbons or where's the reactivity in that structure? The pi bond. That pi bond is associated with what atoms? Both carbons, which means 2 reactive sites. You have to address reactivity of both those sites. If your structure has only addressed reactivity at one of those sites, you have a bit of a problem. Okay, so I saw a couple people draw on, well, bromine. That's good. You've only addressed reactivity directly at one of those sites, but by drawing that structure, you've actually implied another reaction. You implied that there's also a hydrogen there. Take a look at your starting material. Do you see hydrogen? No. Okay. An alkene has 2 reactive carbons. One is negative and one is positive. You have to address both of those reactivities. So it is fine to attach the bromine to one, but then realize that that other carbon is also reactive. Officially, we'd be ending or starting with our 3-membered intermediate structure. That 3-membered intermediate structure breaks open when the second bromide as a nucleophile comes in and attacks. Why would it need to come in and attack? We had a positive bromine that is not a stable structure. We need to break open that ring. Okay? The next layer on top of this, because it could, actually let's ignore that for the moment. Okay? We just have that structure. How about the next one? Moving towards the right. Where do we have reactivity? Hint, it's the exact same site of reactivity as in the previous question, the pi bond. What does a pi bond act as? A nucleophile. It is donating electrons, which means I need to find a positive. Look at the reagents. Do you see a positive? No, at best what you probably see is sodium hydroxide, which should immediately become hydroxide with a negative charge. Why is that now a problem? I have 2 nucleophiles in solution. So maybe I need to use the other structure. What's happening with that other structure? I have 3 very electronegative elements all connected to a single carbon. What happens to that hydrogen? It is now relatively acidic, particularly in the presence of a strong base. So your base can come through and remove that hydrogen Meaning what? What charge would we now have on the carbon? A negative. Son of a... The whole point was to find a positive carbon or a positive atom, and I've still found another negative. What is special about those electronegative elements that are connected to that carbon? Chlorine can stabilize a negative charge better than carbon, better than... What's the other negatively charged atom in our structure? Oxygen. What can happen? We have a leaving group. There's our positive charge. There's our nucleophile. Okay. Just because diazomethane makes three-membered rings doesn't mean it's the only thing that can. Okay. Yes, you are expected to think at that level and see those individual pieces. That is hard. Do not get me wrong. Okay? That is hard, but you know the steps and the pieces to follow through with that. If you saw that on an exam, the very first thing you should do would be, don't cry. Skip it. Don't worry about it. Come back to it later. Okay? Or maybe look at the answers and see if maybe there's a shock of genius hits you because you see that structure. Like, oh my God, that looks incredibly weird. How could that? Oh, that's how it could happen. Okay. But it should be a very quick, you look at it, nope, thank you very much. I'm going to move on. Okay. One of the things that you should be asking me for is not only what you should get on the final, but figure out what that would mean for an ACS score. The ACS exam is 70 questions. Nobody, well, there may be a couple people in this class, need to get 70 questions right. Most people do not need 70 questions right. You need 40. You need 50. It is no longer a 70-question exam. It is a 50-question exam. You have to find your 50 questions. Do not waste time on that question. Well, now you can because you know it, right? Make sense? I will work with you to get you those numbers, but we have to get that level. Is that our question?
Yeah, you said carbon becomes positive?
The carbon becomes an electrophile. Because as that chlorine leaves, we'd be missing its octet. You're right, it's not formally positive. It actually becomes neutral. Okay, so but we've got a carbene equivalent. Next one on the left. What happens? Well, the mercury comes in, we'd form the mercuronium ion. Oh, that's a great leaving group. I don't want that still on there, so what happens? It would want to break off the structure. But to break off, something has to force it off. Do I have a nucleophile? I have the oxygen from my water, which can deprotonate, and I'd end up with that structure, with the mercury attached, officially with the mercury with the O-acetate, or the O-acetyl group.
Why don't we have BH4 in this solution?
I will talk about that later. That's actually is a second reaction step necessary question. So we'll get back to that. Lower right-hand corner, MCPBA. Right? I listed out the letters, but I didn't show it to you, so I real quickly wrote out the formula. We've got that O3. That should be a red flag that you're forming another three-membered ring with the oxygen attached. Okay. Carefully look at each of those structures. Is there something else here that we need to watch out for? Every single one of those has a stereocenter. Okay. Which means stereochemistry needs to be specified all the way through. Okay. Remember, we had a three-membered ring. So where I want you to focus is on the chemistry that you did. The rest of it, who cares about? Focus on the chemistry that you did. Conveniently shown, almost conveniently shown. Give me a second. Conveniently shown in red in all of our answers. That's where you need to keep your focus for your stereochemistry. Everything else is irrelevant. So we take a look at the first structure, those bromines. Okay, I need to specify some stereochemistry on those. Okay, because at this point I haven't specified anything. I could go through and show wedge for the first bromine. It would also show up dashed because pi bonds. So we'll get our enantiomers. Okay. Where's the second bromine have to come in if that one is wedged? It has to be dashed because what did we form? A three-membered intermediate. So having some knowledge of the mechanism behind these establishes that stereochemical relationship. If you don't have that knowledge, you can't answer it. Okay. If we move over to our fun one, the carbene, same deal. Let's go through and show a wedge for one of those bonds. It could have just as easily been dashed. What does that make the other one? It will also have to be wedged. It can't also be dashed. Why not? The spatial arrangement, right? Okay. I have a hand going up. Okay, Jade, now what I need you to do, because you're underneath me, is I need you to touch my hand while still touching my elbow underneath me. Huh? Yeah, because you can't do it. It doesn't work. Okay? Three-membered rings will have to be the same stereochemistry. They have to be wedged. So we get both wedged and both dashed. What else becomes problematic with this? I deleted a carbon. I still have that methyl group. So if those are wedged, where's that methyl? Dashed. Would the relationship be enantiomers between this product and the other one that I didn't show? Why are they diastereomers? There was another stereocenter in the structure that did not change. Okay? So recognizing those patterns can help you through this. Those of you going, well, you couldn't possibly ask all of those questions at the same time. We could. We could just give you the reaction with the reagent and say, what is the relationship between the products? But if you didn't draw any products, exactly. You got to do it, and then tell me that relationship. Okay? So you can be asked to do multiple steps. The mercury one. What's the relationship between our mercury and our oxygen? Remember we formed the mercuronium ion? So I'll show that one as wedged. Where would I expect the oxygen to come from? Has to be dashed because the mercuronium ion with that three-membered ring is blocking the top attack. So the OH has to be dashed. Okay. Knowing the intermediate helps me predict that stereochemistry. Okay. I would also have the enantiomer for this one because there's not a second stereocenter. Last one. If I show one wedged, what has to happen to the other? Must also be wedged. We get an extra kind of dilemma on this one because this structure technically occupies two planes. We have the epoxide right now, that oxygen's coming at you, and then we have the carbons in the plane, right? Okay. I could also draw this structure by, instead of drawing it with the oxygen coming at you, just move it up. Like a game, right? Drawbridge. What happened to the oxygen or the carbons? As the process of them rotating upwards, one's going to be coming at you, the other one going away. I could try and show it like that to help me see it. That's technically the wrong bond angle for that. It'll have to be drawn down but dashed. Build an epoxide, you'll see those bonds have to be drawn down from the structure. It physically doesn't work otherwise. Okay? So, two ways you could draw that structure out. Depending on how the ACS wants to test you, you could be at either one of those for the epoxide. Okay? So be aware of the stereochemical reflexes in the epoxide. Okay? Make sense? Okay. The last question, which was already asked, well, the mercury one, you only showed mercury. What happened to the sodium borohydride? How many people have any idea what sodium borohydride is? Okay. You should, because what should you have already been doing? Reading the textbook to see that when you see the mercury reagent, it is always shown as step 1 and step 2 sodium borohydride. Why do we need that step 2? How many times has mercury ever been shown on any of our structures this semester? None. That's because mercury doesn't want to be on there. We want to get rid of it and get back to our normal, happy, organic chemistry cells. So I don't want to deal with this inorganic nonsense. So what do I have to do? I have to add something to eject the mercury. Okay. The mercury wants its electrons back, which means it needs to take the electrons, which means what charge builds on that carbon? Positive. What would I need to replace it? A negative. What does sodium borohydride supply? Negative hydrogens, also known as hydrides. Okay. Why couldn't a nucleophilic oxygen kick it out? It's not strong enough of a nucleophile to eject the mercury. This is one of the reasons why mercury is so toxic. When it bonds to organic molecules, it stays pretty strongly bonded until you can really eject it. This is why we die from mercury poisoning. Okay. Well, all you got to do is drink sodium borohydride. Don't. Okay. Yes, mercury is dangerous. So is sodium borohydride. Okay. They will both kill you. Okay. Borohydride will probably be faster. Okay. The mercury will just take longer. Okay. So we do need that second step. How do we know we need a second step? Look at your product and be like, do all of those elements look like things that Mike would be somewhat okay with? Oxygen, okay. Carbon, okay. Chlorines, okay. What the frick is a mercury? It doesn't even, symbol doesn't even make sense. We call it mercury and we write it Hg. Okay? So yeah, get rid of it, burn it with fire, add your sodium borohydride. Okay? So when you go through and do a mechanism, if you see a piece that you don't think belongs there, you will likely have to do a second step. Okay? Four-membered transition states. Okay? For this subclass, we need a very small leaving group. Br2, does that have a good leaving group? Yeah, it has a great leaving group. Okay? Would that be a small leaving group? No, it's a great leaving group because it's really big. Br2 does not fit in this category of reagents. So, gone. How about this one? That has the exact same conditions going on with Br2. Okay? Equal electronegativity, that bond can polarize one direction over the other. Okay? If I brought an alkene near it, that would cause hydride to act as a leaving group. Can hydride act as a leaving group? No. So what has to happen? I have to fit into this new category where my leaving group immediately attacks the alkene. Because it immediately attacks, what does that mean the arrangement of the hydrogens are on that new alkene? They're on the same side of the double bond. With a three-membered ring, we got them on opposite sides with that secondary attack. With the four-membered ring, it has to form on the same side. That's because your leaving group isn't stable enough to go around to the other side. Okay? So we get that same side attack. How about the next one? What the F? So number one, does anyone know what OS is? Oh, please save me. And there's too many letters. Okay, OS is osmium. Okay, 76. Okay, organic chemists can't count that high. That's not a pleasant reagent. But osmium, being a transition metal, does all sorts of goofy stuff with the oxygens. It will facilitate an alkene attacking one of the oxygens. Then what would the leaving group be? Could it be the osmium? No, because I can't break two bonds. It only exceeded by 2 electrons. What would I have to break? A single pi bond. I'd be breaking one bond. Okay? So my leaving group is 2 electrons. Are those stable? No. So what do those electrons do? Go to the osmium. But osmium is like, I don't want 2 electrons. Well, fine. If you're going to give them to me, I'm going to have to get rid of something else. All of that has to happen at the same instant. Why? Our leaving group is a pair of electrons. Is that big? No, that's insanely small, which means those two oxygens have to attach to the pi bond at the exact same instant on the exact same side of the pi bond. Right? Just like our hydrogens. Okay, so what we're trying to do is again find patterns that allow us to see what's going on with these. That doesn't make them obvious by any stretch of the imagination. Okay, but what we're trying to evaluate is what is happening in each of these cases. So when we go through and look at the two reactions shown here, we switched this up and I got rid of the dihydrogen. That sounds really stupid. Hydrogen gas, and switched it to boron. What would our leaving group be in this case? Boron. Is boron a good leaving group? No. Insanely tiny, smaller than carbon, less electronegative than carbon. Everything about boron screams bad leaving group. Okay, so boron can't leave on its own. So if our alkene comes in and forms electrons or makes a bond, we're going to have to break those bonds at the same time. It turns out that our boron actually acts as the electrophile in this case and not the hydrogen, which does seem a little bit weird, right? We always see hydrogens as positive. Why is the boron positive? Well, its starting structure is BH3. What is that hybridization? SP2. What is left over? A p orbital, and in particular, an empty p orbital. What can I put in that empty p orbital? Pi electrons. So my pi electrons from my alkene immediately come out. That's an eraser. Immediately come out, share with the boron. But now boron has too many electrons, so it has to eject a leaving group. The only thing it has to eject would be hydride. Is hydride a good leaving group? Nope. So where does the hydride immediately go? Back to the alkene. The result is what we've got shown with all these dotted lines. Okay? We are forming effectively a four-membered ring transition state. Okay? We never form the formal four-membered ring because they're all single bonds. What happens when we move to the osmium structure? Well, osmium being that obnoxious thing can mess with our oxygens. The pi bond can come out, form a bond with one of the oxygens. That then must eject pi electrons over to another oxygen, which means that oxygen has to ditch electrons out to our carbon. The result is we end up with a five-membered ring intermediate, not a transition state. Why do I have now an intermediate and not a transition state?
Because five-membered rings are more stable than four?
Five-membered rings are more stable, but that's not why. What bonds do we break with the boron structure? Sigma bonds. What bonds do we break with our osmium structure? Pi bonds. That's why we can form an intermediate. Okay? When you get rid of a sigma bond, you can't have an intermediate as a ring because you literally lost that sigma bond. You can do it with a pi bond because when you get rid of the pi bond, what's left over? A sigma bond. Okay? So you get these really kind of goofy, weird things happening. Chapter 24 largely talks about these cyclic intermediates. Right? That's your osmium structure. Ozone falls into that category. Potassium permanganate. Okay? So you get a lot of these really larger, extended structures, and it's largely because metals are irritating to deal with. Those d orbitals really mess with the chemistry and make it harder for us to build patterns around that match our Lewis structure understanding. Okay? So looking at our boron region a little bit more carefully, if we look at our Lewis structure, there's that empty p orbital. Okay? So what happens when we bring in a butene? Okay, well, the butene aligns as such. Okay, they're on the same side. The pi electrons from our butene can share with the boron, leaving behind a carbocation. We would have also exceeded the octet on our boron, because boron's happy at 6, which means it has to eject that sigma bond. And it ejects that where? Immediately into the forming pi system. what would the resulting structure look like? Like, oh God, I don't want to draw it. But I'm a horrible person, you're going to draw it anyway. Or I'm not a horrible person, that's why you're going to draw it anyway. Whichever makes you draw it. And I'll give you some hints. Those are horrible hints. Take a look at the hints that I drew. What did I draw on the hint? I drew the hydrogen and the boron in the plane of the paper, trying to keep things nice and simple. Just having that drop in immediately. Notice the hydrogen and the boron are both the same side because all happened at the exact same instant. They all had to be there at the same instant. Okay? So I even went through and color-coded. The new bonds I showed in red. The old bonds I showed in black. What am I missing? The methyls. Did the methyls do anything in the course of this reaction? No. Which means, what should I do with them in the product? Show them in the exact same location. Okay. Didn't touch them. That's a sigma bond, right? If it's a sigma bond, couldn't it have rotated so that I would have had one wedged and one dashed? That seems reasonable. When did I have a sigma bond? After the reaction. Okay. The only time the sigma bond was allowed to rotate was after the hydrogen and the boron were already added to the structure. This all happened at the exact same instant. Okay. So I could potentially show those as wedged and dashed. But if I did so, it would have to look something more along these lines. Okay, well, now I'm showing a different product. Am I? No, it's the same product. Okay. The orientation of the hydrogen and the boron are still held constant. Because this reaction happens simultaneously, the arrangement of your groups in the starting alkene are locked into position in our final product. We cannot get a rotation on it. This becomes an interesting observation, because when we did the acid reactions with our alkene, what could happen? Everything. Everything could happen. The hydrogen could attack or be attacked and placed top or bottom. Then the bromine could be placed either top or bottom. So I got a whole smattering of possible products. Okay, well, it turns out here, I don't. Okay? Because this reaction all happens at the exact same instant, I only get two products. One where the boron reacted with the top side of the p orbitals, the other one where it reacted with the bottom. Either case, the orientation of the boron and the hydrogen is such that they added to the same side of the double bond. Even this bottom structure down here is identical to the top one. But it's dashed and wedged. I rotated the structure. If you rotate that single bond back around, you end up right back with the starting structure. These are not two different attacks. Okay? So this is where we really bring in the idea of the syn and anti-addition reactions. In the acid-base alkene additions, we didn't worry about it because Well, it wasn't relevant. All those possible attacks were there. Right? When we formed the three-membered rings, we did a syn addition. We had to form the three-membered ring where they were both wedged. What's happening with this four-membered transition? They're getting added at the same time, which means we're doing a syn addition. That syn addition dictates the stereochemistry in the products. Would the ACS exam show you the top product? Probably not. They're actually probably going to show the bottom one. Why would they show the bottom one in favor of the top one? So we can get all kind of sneaky and backhand on this because they're jerks and they're trying to trick us. The top structure is actually a bad structure to draw. If you look at the Newman projection, that drawing is an eclipsed conformation. And what do we know about eclipsed conformations? They're higher in energy. They're so high in energy, they're actually transition states. Those are not valid structures to draw. They would probably do the rotation, not because they're trying to be complete and utter dicks, but it's the appropriate way to draw the structure. Okay? We can still call them dickish. That's fine. Dickish. I like that. You're kind of dickish. Okay? Does that make sense? So we have to be aware of those extra sigma bond rotations and aware that it may very well confuse our resulting structures. Be careful with these additions. It becomes very important to recognize that you're getting a syn versus an anti-addition. Make sense? Okay. Do we need second reactions? Well, we talked about it with the mercury. Right? Yeah, I want a second reaction with the mercury because I don't freaking know what mercury is. Get rid of it. Right? If we drew out the other one, conveniently I erased it, right? What did we end up with as a theoretical product? We had the boron and our hydrogen. How many times have we talked about boron? A little bit more than mercury. Right? But boron isn't a fun structure to have on there. We want to get rid of the boron. So what do? We get rid of it. Okay? We have to eject it. Okay? We will do that by reacting that species with peroxide. It must happen in a second step. Okay? So what we're seeing now is two-step reactions. The boron reagent in step 1 and then peroxide in step 2 together do the complete reaction. Okay? The mercury in step 1 and borohydride in step 2 together do the complete addition. With the mercury reaction, what did we add? Well, we added OH followed by H. We added water. With the boron reaction, in the first step we added H. In the second step, what do you see a lot of? There's an awful lot of oxygens in there, right? That's because we're adding OH. We're adding the exact same things. Huh. Why the hell do I need two reagents if I'm adding the exact same thing? Because those two pieces get added in different locations. How do I know which location they get added to? Look at resonance. Look at differences in electronegativity to predict your charges for each of those species. Okay. The boron reagent is typically referenced as a anti-Markovnikov addition. Anti-Mark. The other one, the mercury reagent, is typically known as Mark Kovnikov. Does that make you happy? That says Markovnikov. Okay. Why are these anti and Markov? One's following the rule, one's not. I don't understand. The hydrogen added in the boron reagent was what charge? It was negative. the hydrogen added in our mercury reagent, or sorry, the oxygen, actually the oxygen added. Ooh, man, dicey, can't pull that. Damn it. I really wanted that. Wanted that to work. It didn't work out for me. If we look at our initial step when these reactions happened, okay, that first step, the hydrogen came in as a negative, the boron came in as a positive. Okay, so what we had to cleave off was that positive boron. And the other one, our mercury came in, our oxygen rather came in as our negative, and our mercury was our positive. Okay, so that first step is what's dictating the chemistry. Where does the negative atom go? To the most positive carbon in our alkene. The other atom goes to the other location in our alkene. When you draw your alkenes and overlay that negative information in it, you'll notice that that first step is what's going to dictate the location of the hydrogen and the oxygen relative to each other. Okay? However you want to memorize or deal with that is up to you. You have the mechanistic foundation right now to do that. It's just a question of working through that. Okay? So if we looked at our mercury, what happens? We form that mercuronium ion. Where does the oxygen then come in and attack? The more substituted position. That's what it's kicking out. Okay? If we look at our intermediate from our boron reaction, so both of these are starting with this structure. So this is our mercury, this is our boron. Okay? We're adding a hydride. The hydride needs to go to which position of our alkene? The positive. Which one's the positive? The more substituted. Yeah? What happens as we progress through? You'll notice the oxygen is now the more substituted in our mercury. And our next step for the boron, what happens? We add our hydroxide to do what? Eject the boron. What's the end result? The location of the OH versus the hydrogen are at different spots. If you evaluate your resonance and your mechanism, you can evaluate where those individual groups go. If you choose to not evaluate the mechanism, you are fine to do so. That is now memorizing that the boron reagent is Markovnikov and the boron reagent is anti-Markovnikov. You can tell how well I memorize it. The boron reagent is anti-Markovnikov and the mercury reagent is Markovnikov. Okay? And a lot of it has to do with the fact that Markovnikov did not know electrons existed, which means there is no resonance. All he's looking at is the location of those atoms, and the identity of those atoms becomes questionable when we go through and evaluate these things. Okay? So with our mercury reagent, we need hydride as a strong nucleophile. Okay? It is supported by our boron. So when this reaction happens, the mercury reacts with the boron, which ejects hydride back. We get another four-membered ring transition state. Yay! Just because we did it once doesn't mean it disappears. It comes back. Okay? And the end result is that we've added hydride, or an apparent hydrogen, to the position that had the most hydrogens. Okay? And the oxygen to the position that had the least hydrogens. The same kind of thing happens in the reverse with our boron reagent. Okay. Our peroxide comes in. It's still a boron reagent. This is, by the way, not the right mechanism, but it's close enough. Okay. We have our empty p orbital. The electrons can donate in. Electrons donate out. And we generate the oxygen. The interesting thing with the boron reagent that becomes very, very important is the end result for both the hydrogen and the OH is that they are added to the same side of the pi bond. The initial addition, sure, fine. You're like, yeah, I knew that was same side. Remember, that was an intermediate that we didn't evaluate. What we want to look at is the final product. In the final product, the hydrogen and the OH are added to the exact same side, largely because boron facilitates all of those reactions. And boron allows the reaction to happen simultaneously at that spot, which is why we get the retention and stereochemistry of that. That is a super common ACS question. Okay? So if we looked at some examples, what would we get for the first one? Well, there's our ring. We had the double bond. I need to add, because it's boron and peroxide. The raw memorization is that reagent adds hydrogen and OH. So I can add my OH, and I could add my hydrogen. How does it add them? Look at our mechanism. Because of boron, they are always added on the exact same side, all the way through. Which means if the OH is wedged, the hydrogen is wedged. Is it necessary to specify that for this first reaction? No, why not? There's no stereocenter. Okay? Where I placed that hydrogen, there's another hydrogen there, which means that's not a stereocenter. I didn't need to specify that, which then also means the other carbon is also not a stereocenter. That one's not important to evaluate RH versus OH. How about the next one? We're still adding H and OH. This one now becomes a little bit trickier because are the carbons of the pi bond identical? No. Right? How does the boron reagent add the H and OH? In an anti-Markovnikov fashion, one thing you could go through and do is if you equate this to just being H and OH. Okay? The boron reagent does the opposite of what you would expect. What? Well, what do I expect? If you draw resonance for your alkene, where's your positive charge build? Positive, negative. Where would you expect the hydrogen to go then? What charge would a hydrogen typically be? Positive. So I would typically expect the positive to go where the negative is. Because it's the boron reagent, I need to remember that it adds H and OH and it adds it the opposite of what I would expect. If I would expect the hydrogen to go to the negative, where should it go? To the positive. Where should the OH go? To the negative. Horrible. I don't like that. But it works. Right? The next part, is there a stereocenter? So let's continue to add the rest of the atoms. Is there a stereocenter? No. Do I care about wedges and dashes? No. Next one. Right? If I think resonance, what would happen? Positive and negative. Oh, it's boron. I got to do the opposite of our H and OH addition. So boron reagent, I'm adding H and OH. What would be the opposite location? Well, the H should go to then the positive location. Where should the OH go? The negative. Is this one I now need to worry about stereochemistry for? Yes, there's two stereocenters. So if I make the OH wedged, what has to be the hydrogen? Also has to be wedged because of how it adds. You got to remember the boron adding to the same side. That makes the methyl dashed, and we would have our answer. The last one, I'll just draw it out and then leave you guys to deal with it. I would count out carbons as soon as you see a triple bond. I've got 4 carbons. 1, 2, 3, 4. That's my answer. Okay? we will pick up there on